Good time of day, dear students. I hope that every one of you is feeling well, and for those who are not feeling well, I wish good health. Today, the topic of the lecture is the heat engines. As you may know, the power engineering specialty are studying the heat engines as the main source of mechanical energy. There is other types of sources of mechanical energy, like the electricity, which is converted in the electrical engines to mechanical energy. But generally, to get the electricity, we are using the heat engines. The most common heat engines are presented in the following slide. The power cycle, heat engines, the Rankine cycle. The Rankine cycle, you studied the Rankine cycle in your student independent works. Rankine cycle is mainly the cycle that uses water vapor, and steam, right? Which is steam turbines generally. In Rankine cycle, we heat the water to the boiling point, then we superheat it to the point where we get the maximal efficiency. The Carnot cycle. Well, generally, directly we are not using the Carnot cycle. We are using the cycles that are close to the Carnot cycle. The Carnot cycle is presented as one of the ideal cycles, which has the highest efficiency among the heat engines that are presented in the list before you. Otto cycle. The Otto cycle is the cycle that used in excuse me. Otto cycle generally used in internal combustion engines, which are widely used by the transport system. I'm pretty sure that you know well the internal combustion engines generally used in vehicles, right? Diesel cycle. The diesel cycle has the same cycle, very close to the Otto cycle, with one little difference. The process of combustion and ignitions is done by itself, which means that when we're using diesel gasoline, it combusts itself due to the high temperature and pressure occurring in the cylinder of the internal combustion engine by the work of the piston. Stirling and Ericsson cycles. Well, generally, Stirling and Ericsson cycles are considered as the external combustion engines. So they work as the internal combustion engines with one big difference. The heat is given to the cycle from the outside. We will consider it very closely in the following lectures. Brayton cycle. Well, your second student independent work will be in the calculation of the Brayton cycle. Brayton cycle is the cycle of gas turbines, which are widely used in every part of the world except from Antarctic, right? So the Brayton cycle is the gas turbine cycle. In our country, there is no much of the gas turbines, but they are widely spread in the western regions where the oil and gases are where we get the oil and gas, right? And jet propulsion cycles. Jet propulsion cycles is the cycles that are widely used in the airplane construction, and most widely in the jet fighters. We will consider them very closely in the following lectures. So today we're gonna see the three cycles: Rankine, Carnot, and Otto cycle. The Rankine cycle, the for vapor power cycles. In these pictures, we can see the picture of the Rankine cycle, which consists the pump, the boiler, the turbine, and the condenser. The Rankine cycle and the TS diagram of this cycle. As you can see from the picture, the cycle works as following. The water water is pumped in a pump. Then the pumped water goes to the boiler where it heats, vaporizes into the superheated steam. Then after that, the superheated steam moves to the turbine and rotates the turbine, and the turbine is connected to the electric generator, which generates electricity, right? Then the saturated vapor is goes to the condenser where it condenses, which is displayed by point 4 and 1. The pump work is depicted by 1 and the first and the second points. The work of the boiler is not shown here, but generally it's point 3, point 4, and point 5. You know, and this is the saturation line, right? 3 and 4 points are the work of the steam turbine. As you can see, the ideal Rankine cycle consists of this following processes. 1 and 2, isentropic compression in a pump. 2 and 3, constant pressure heat addition in a boiler. 3 and 4, isentropic expansion in a turbine. 4 and 1, constant pressure heat rejection in a condenser. Heat rejection means that we give some part of our heat that we got from the fuel to the environment, right? How can we calculate the ideal Rankine cycle? Here we can see the work of the ideal Rankine cycle. The pressure after the pump is equal to 3 megapascals, and the temperature after the boiler is equal to 350 centigrades. And the pressure in the condenser is 75 kilopascal, which is pretty high, to be honest. We must determine the thermal efficiency of this cycle. As you can see, to determine the thermal efficiency, we need to determine the amount of heat given to the cycle and the amount of heat rejected from the cycle. So first we got the saturated liquid right from the condenser, which is equal to 75 kilopascal. We will find the enthalpy and the specific volume of this liquid. Then the liquid goes to the pump, where it pumped to the pressure 2, which is 3000 kilopascals, which is 3 megapascals. The amount of heat that we used is found out by this formula, which is the amount of heat given to the water. Then secondly, we heat the water to the aimed pressure and temperature, and we find the enthalpy. After that, we get the enthalpy of the saturated vapor, right, by the pressure of 75 kilopascal, saturated mixture, which is 2403 kilojoules per kilogram. The amount of heat given to the cycle is the difference between the superheated vapor and the saturated liquid. The amount of heat given to the environment is the difference between the saturated mixture minus the pumped water, 348. Thus we can find and thus we find the thermal efficiency of the cycle and is equal to 26%. The actual vapor power cycle differs from the ideal Rankine cycles as illustrated in figure 4a as a result of irreversibleness in various components, fluid friction and heat loss. Fluid friction, it means that we lose energy by the forces of friction, and heat losses, we're using some part of the heat to the environment in different parts of this cycle. This requires a large pump and water into the pump. The water must be pumped to a sufficient higher pressure than the ideal cycle calls for. Well, when we pump the water in real cycles, the pressure of the boiler, for example, if the pressure of the boilers is 20 megapascals, we are pumping the water to approximately 25-27 megapascals. Why? Because we're using some part of the pressure during the movement of the water or steam in the heat in the pipes of the boiler. So it's friction losses. Thus, these losses are giving us this that we are losing some part of the energy, usable energy. For example, the actual steam turbine is calculated in this formula. In this example, a steam power plant operates on the cycle shown in figure 10.5. I showed the picture. If the isentropic efficiency of the turbine is 87% and the isentropic efficiency of the pump is 85%, determine the thermal efficiency of the cycle and net power output of the plant for a mass flow rate of 50 kg per second. So we have the pump, but we know that some part of the energy is lost to the environment. So we're using the thermal efficiency of the pump, which is 85%, which means that we are losing more energy, right? We are giving more energy to the actual cycle compared to the ideal. And the turbine work. Well, you all calculated the work of the turbine, the efficiency of the turbine minus the enthalpy on the inlet of turbine and the enthalpy on the inlet of the condenser. So the boiler gives us the energy 3647 minus 160, which is 387 kilojoules per kilogram. So the net efficiency is the difference between turbine and the energy used in a pump. So the efficiency of the thermal efficiency is the 36%. Without the irreversible, the thermal efficiency of the cycle would be 43%. Please, if you have any questions, you may write it down on a feedback section, which I will add after this lecture. The Carnot cycle is composed of 4 totally reversible processes. Well, in real cycles are not reversible, but here they are reversible, right? That means that the cycle is ideal. PVTS diagrams of the Carnot cycle are presented in the pictures. As you can see, the isentropic means the S is constant. Isothermal, it means that T is constant, right? The isothermal process in PV diagram is shown by these lines. Thus, this is the same for the TS diagram, right? Isothermal, isentropic. Otto cycle, the ideal cycle for spark ignition engines, right? The spark ignition engines generally they consist of the 4 strokes. In the top picture we can see the real one, in the lower one we can see the ideal cycle. So the isentropic compressions means that when we compress some fluid or liquid, the entropy of this liquid doesn't change, which is impossible, right? Because we are generating the entropy by the friction processes, which means that we have a friction which transfers the potential energy or mechanical energy into the heat, which increases the entropy of the fluid and the system generally. So isentropic compression. Then we have isochoric compression, which means that we have the constant volume and the temperature rises, which is impossible too, as we will see it in the following pictures. Then we have the working process, isentropic, which is impossible too. Some part of the heat is lost to the environment, to the friction, and other ones. Then we have the heat rejection. In the top we have the real process, compression stroke. Here we have the compression process of air-fuel mixture. Then we have the process of ignition of our fuel and the expansion. Then we have the exhaust stroke, when the gases leave our compressed or our cylinder. Then we have air-fuel mixture, the process of intake, right? Our the cylinder piston goes down. Here we have the PV diagram of the Otto cycle. Here we have the intake, right? So we intake the volume, intake the air-fuel mixture. Then we compress it. This is the first track. This is the one. Then the second one is the compression cycle. Then in some part of it we got the ignition cycle, which increases the pressure, right? Because we have the combustion processes. Then the end of combustion, then we have the expansion, which means that the gases, due to the high pressure, turns the piston down. Then the volume of the gases expand, and after that the piston goes up. Then we go to the exhaust, which means that the gases are leaving the cylinder. Thus, the work of the ideal and the real actual spark ignition engines, or the Otto cycle engine. Well, that's the end of the lecture. In the following lecture we will end by studying the other cycles. If you are interested, please prepare the presentations for explaining the work of this cycle. Thank you very much. I hope we meet again, not in a following year, by end of this year. Goodbye and good luck.